It is considered one of the most challenging topics to master, and most people desire to be comfortable with IP addressing and subnetting. In this class, we're going to cover the basics of IP addressing, from what is an IP address, the structure of an IP address, to more complex issues such as converting between decimal and binary, the famous subnetting, and we're going to close off by designing our own IP address scheme. The objective of the course is to take someone who has little experience about IP addressing to a point where they're comfortable and confident in being able to design their own scheme. The class is targeted towards anyone who's got an interest in IT. So without much further ado, let us begin.
So what is an IP address? It is an address that uniquely identifies a device on the internet or a local network. In order for us to understand, we need to look at the different types of addresses that we deal with on a day-to-day basis. Most of us have a home address. This is where we reside. We use that address to send and receive items. It could be utility bills, online purchases. That address is what your local post office uses to identify your house amongst other houses in your neighborhood. The other form of address that all of us have is an email address. We use our email addresses to send and receive emails. Servers across the world route emails based on that particular address. So we're getting to understand that an address is a very important component and it must be unique. IP addresses allow devices to communicate over the network. They are used to route packets from source to destination, and the internet depends on IP addressing in order for it to function. You will notice that our addresses have different formats. Now that you understand what an IP address is, we're going to look at the structure of an IP address. There are two types of IP addresses, IP version 4 and IP version 6. We're going to be focusing on IP version 4. An IP version 4 address is 32 bits in length, and it is usually written in a format known as the decimal dotted notation, which is shown on the screen, and is usually pronounced as 192.168.0.254. The address is split into 4 segments, each separated by a dot. Each segment is 8 bits in length, and 8 multiplied by 4 gives us a total of 32 bits. Each segment is known as an octet or 1 byte. These terms can be interchanged when defining an IP address, so be sure that you're comfortable with the different terminology. The value of each octet ranges from 0 to 255. So if we look at our diagram, you'll notice that I wrote the address in the dotted decimal notation on the top, and then I wrote the equivalent in binary. But I separated the bits into 4 segments. We have the first byte, the second byte, the third byte, and the fourth. A byte is equivalent to an octet, and each octet is 8 bits. So when we add that all together, we come up with 32 bits or 4 bytes. We have the network portion and the host portion. The network ID identifies the network, and the host ID identifies the individual device on the network. In our email example, we have the username, that is John King, then we have the @ sign, and lastly we have the domain name, and in our case it is gmail.com. The @ symbol or sign is what separates the username from the domain name. So any email address with the same domain name would belong to the same network. The network ID is similar to the domain part of the email address in that any IP address with the same network ID would belong to the same network. The host ID, on the other hand, identifies the individual device on the network, and it has to be unique because you cannot have 2 IP addresses that are identical in one network. Whilst it is easy to identify the username and the domain part of an email address because they are separated by the @ sign, it is not easy to do the same with an IP address. I want you to take a guess. Which part of the address is the network ID and which part is the host ID? You can pause this video and take your time. Unfortunately, there's no way to tell. We could try to use the classful boundary of the address, such as class A, B, or C, but that will not be accurate. We need something that draws the line and tells us which part of the address is going to be the host and which part will be the network portion. A subnet mask is what we use to identify which portion of the IP address is going to be the network ID and which portion will be the host ID. In our example, the subnet mask is 255.255.255.0. This basically means that we are going to use the first 3 octets or the first 24 bits of the IP address to represent the network ID and the last 8 bits for the host ID. If we count the first 3 octets and draw a line, it means that 192.168.0 will become the network ID and 254 will become the host ID. The subnet mask is not a fixed value. It can change. So with a mask of 255.255.0.0, our network ID will change to 192.168 and the host ID would be 0.254. Later on in the course, we'll cover subnet masks in more detail. When I turned 18, I was excited because finally I could get my driver's license. But before I could jump into any car, I had to learn the road rules. This included learning about which side of the road to drive, which cars to give way on a T-junction, what to do when you see a stop sign. Now, why is this important? Because every address standard has a set of rules that need to be followed in order for things to work. I'm sure if you try to send an email without the @ sign, that email is going to bounce because email addresses require the @ sign for the address to be valid. In order for IP addresses to be valid, there are a number of rules that must be followed. Rule number 1, the host portion of an IP address cannot be set to all binary zeros because that is used to refer to a network address. We will look at network addresses in detail later in the course. Rule number 2, the host portion of an IP address in all binary ones represents a broadcast address. This is a special address that is used to send packets to all hosts on a particular network. Rule number 3, the network ID of 127.0.0.0 is reserved for diagnostics and testing. The famous address 127.0.0.1, also known as the loopback address, is used for testing network card. Rule number 4, an IP address of all zeros is used to represent something known as the default route. And the last rule, an IP address of all ones is used to represent a broadcast to all hosts on a particular network. These rules are important for you to understand. Now that we have looked at an IP address and subnet mask, we now need to check the IP address on our computers. They say that the best way to learn is when you practice. I'm using a Windows machine. If you're using a different operating system, just check online on the steps of how to check your IP configuration. On Windows, there are many ways to get to command prompt, but this is the one that I find easiest. Go to Start, type Run, press Enter. In the pop-up box that comes up, type CMD and press Enter. This should take you into the command prompt. Whilst in command prompt, type our command IPconfig and press Enter. A lot of information is going to show up on your screen. We need to focus on the adapter or network card that you're using to connect to the network. Under the adapter, you will see an IPv4 address. Mine is 192.168.0.3 with the subnet mask of 255.255.255.0 and my gateway is 192.168.0.1. This means that my network ID is going to be made up of the first 3 octets or the first 24 bits of the address. So my network address is 192.168.0 and my host ID is .3. So for now, I want you to write down your IPv4 address, write down the subnet mask and your default gateway. The next step is going to involve you opening up a browser on your PC. It doesn't matter, it could be Google Chrome, Microsoft Edge, Internet Explorer, Firefox, whatever browser that you have. Just open the browser and go to the default google.com webpage. In the search bar, I want you to type what is my IP address and press enter, and an IP address should show up on the screen. Mine is 42.241.239.1 and the address on your screen is your public IP address. That is the address that you use when you're on the internet. The first one that we found in command prompt was our private address. Later on in the course, we're going to look at the differences between private and public addresses. Earlier on, I mentioned that our IP address can be written in either decimal or binary. In order for us to be comfortable converting our addresses from binary to decimal, we need to learn about the two numbering systems. A little bit of math is going to be required, but trust me, it's going to be nothing hectic, and we're going to walk through together along the way. We have two numbering systems, binary, which is used by computers, and the decimal system, which is what we use in our everyday life for counting. In the decimal system, we use 10 different numerals from 0 to 9, and these are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9, just in case you forgot your primary school math. When we get to the number 10, we have no numeral to represent this value, so it is written as 10 and read as 110 and 0 units. The idea is for us to use a new placeholder for each power of 10 to make up any number that we want. So the number 134 in decimal means 100, 3 tens, and 4 units, although we read it as 134. As shown on the screen, we have 10 to the power 0, which is equals to 1, and that represents the units. We have 10 to the power 1, which is equals to 10, and that represents the tens, and 10 to the power 2, which is equals to 100, and that represents the hundreds, and so on. In the decimal system, we saw that 10 numerals were used. Because computers work in binary, and binary only uses two numerals, 1 and 0, our placeholders in binary increase by the powers of 2. So the first place has a value of 2 to the power 0, which is equals to 1. The second one is 2 to the power 1, which is equals to 2. The third would be 2 to the power 2, which is equals to 4, and so on. This sequence is very important for you to master because it's going to help you along the way. I have put a table for us to practice. On the top row, we have the binary exponent, and below, we have the decimal value. So starting from the right to the left, these are the increments that we get when we're counting in powers of 2. We have 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, 4096, 8192. But for now, we are interested in the first 8 values, or up to 128. If you want to master IP addressing, you need to commit this sequence to memory because you're going to use it quite a lot when subnetting and troubleshooting IP address issues. If I lost you somewhere along the way, please stop this video, rewind it, go through again, because this is the foundation of IP addressing. In the next video, we're going to be converting our addresses from binary to decimal. There are many ways to do this, but I found it simpler to use the table for reference when you're starting. Later on, with practice, you can learn to do it in your head. Remember, an IP address is 32 bits broken into 4 octets, and each octet is 8 bits. Step number 1, we are going to draw a table with 8 columns and 3 rows. In the first row, we are going to put the first 8 values of our binary counting system in each column. That is 2 to the power 0 up to 2 to the power 7. Below that, in the second row, we'll put our values 1, 2, 4, 8, 16, 32, 64, and 128, starting from right to left. Now, all we have to do is just basically place our binary digits of our IP address into the respective columns. When we're working with binary, a bit can only be a 1 or a 0. 0 equals to off, 1 is equals to on. We're only going to add the columns with the bits that are turned on and ignore the ones with zeros. In the example that I put on the screen, we have a binary value of 011010000. So we only have 3 bits that are turned on, and these are 64, 32, and 8. So to get the decimal value, we are going to add 64 plus 32 plus 8, and that gives us 104. To convert the full address, we have to take each octet separately and write it in the table as follows. Then we have to add all the columns with the bits that are turned on. I've already written the binary of each octet and have placed them in the table. Octet number 1, we're adding 128 plus 64, which is equals to 192. Octet 2 is 128 plus 32 plus 8, which gives us 168. Octet 3 is 8 plus 2, which is equals to 10. and the last octet only has one value under 1, so we're not adding anything. When we are done, we then take the decimal values and then write them in dotted decimal notation, and we get our IP address of 192.168.10.1. So our binary address is equivalent to 192.168.10.1 in decimal. I hope that was easy to convert. Let us try another one. This time around, I want to encourage you to pause the video, try and do this on your own, and then watch whilst we work through together. The binary address that we're going to be converting is 10.101.000.001.000.0000010. Let's work through together. First, we will draw our table, but this time around, try not to use the powers of 2, but just try and put the values 1, 2, 4, 8, 16, 32, 64, 128. Next, we will write our binary value into each column, and then we'll add. Octet number 1, we're adding 128 plus 32 plus 8 plus 4. That gives us a decimal value of 172. Octet 2 only has one bit that is turned on, which is 16. Octet 3, we're adding 64 plus 32 plus 4, which gives us 100. And the last octet only has one bit that is turned on, and that is column number 2. So our binary address converts to 172.16.100.2 in decimal. One more example, but this time around, we're not going to draw the table. We're going to try to do this from memory, and that should be easy. The first octet only has one value of 128. The second octet, we are adding 8 plus 2 plus 1, which is equals to 11. Remember, starting from right to left. Third octet, we're adding 2 plus 1, which is equals to 3. And in the last octet, we're adding 16, 8, 4, 2, and 1 to give us 31. So our IP address is 128.11.3.31. Now that we have mastered converting from binary to decimal, in the next video, we will look at converting from decimal to binary. Thank you for watching, and I will see you in the next one. In the previous video, we looked at converting binary to decimal. This time, we're going to do the opposite. The process is similar. The only difference is that we are identifying the bits that we need to turn on in order to get our decimal value. Once again, we're going to start by drawing our reference table. Then we're going to take our decimal value and decide which columns in our table do we need to turn on in order to get our decimal number. In our example, the first decimal value is 192. So we need to figure out which numbers do we need to add to get 192. In this case, we add 128 plus 64 to get 192. We are going to turn on the bits under 128 and 64 and then put zeros for the rest. One thing to note is that for the numbers that you don't need, you put a 0, and for the numbers that you need, you put a 1. Let us look at the following address, 172.16.10.1. For us to get 172, we need to add 128 plus 32 plus 8 plus 4. So we're going to put 1s under those numbers, and we're going to put zeros for the rest. So our binary value equivalent would be 10101100. Let's look at 16, and that's probably much more easier. We already have 16 in the column, so we don't need any other number. For the number 10, we're going to need to add 8 plus 2, and for 1, we only need a 1. So our binary should look like this. The next step is now to write it in a continuous 32-bit value. I have just separated it for ease of visibility, but the correct formatting has no spacing. So 172.16.10.1 is equals to the binary value that you can see on my screen. Let's try another address, 192.168.1.254. This time we're going to do it a little bit faster. For 192, we add 128 plus 64. So we turn those 2 bits and zeros for the rest. For 168, we're going to need 128 plus 32 plus 8. And as for 1, straightforward, we only need 1 bit. And the last one is 254. And we're going to add everything except the last bit of 1. So our binary value should look something like this. Please take time to practice this until you can comfortably convert an address from decimal to binary, or the other way around, without having to draw the reference table. Try doing it in the head. In this section, we have covered what is an IP address. We looked at the structure of an IP address and how that is important for us to understand. We also looked at the rules of IP addressing, and we closed off by converting our IP address from either decimal or binary. Thank you for watching, and I will see you in the next one. There are two types of IP addresses, public and private. For us to understand the difference, we'll need to rewind time to when the internet started. In those days, if you wanted your computer to be on the network, you had to make an application to an internet registry organization for an IP address block. They would review your application, and if granted, they would allocate you a block of unique public IP addresses that were routable on the internet. You would then assign these addresses to your devices, and they would also be reachable online as these addresses were public. As the internet began to grow, it grew fast beyond anyone's expectation, and demand for IP addresses started to increase. There were concerns that globally unique public IP addresses would be exhausted. So they decided to come up with a block of addresses that were going to be private and not routable on the internet. So IANA, who are the Internet Assigned Number Authority, reserved the following blocks of IP addresses for private use. Any IP address that falls in this range is considered a private IP address. Because these addresses are private, anyone can use them without having to apply to any registry organization. This means that different organizations can use the same IP address block without any conflict. If you look at the IP address on your computer that I asked you to write down earlier, you'll notice that it falls into one of these three categories. But when you look at your public IP address that you got from Google, you'll notice that it doesn't belong to any of these ranges. Mine was 42.241.239.1. The IP address on your computer is a private address and is not routable on the internet. So in order for you to go online, you need a routable IP address, which your internet service provider allocates to you, and this is known as the public address. So the difference between the two is that one is routable and the other is not. In the next video, we are going to look at the different IP address classes. Thank you for watching, and I'll see you in the next one. Not all networks are created equal. Some are large with many devices, some are small. In the previous video, we mentioned that if you wanted IP addresses, you'd make an application to an internet registry and they would allocate you a block accordingly. This block size was based on the size of your organization and how many devices you would have on your network. The designers of the internet decided to create IP address classes for networks based on size. The objective was that each class would be different in size and therefore meet different needs. The simplest example that I could probably come up to help you understand this concept is the different classes you find on a commercial flight. There are about 3 classes. You got first, business, and economy. And these classes cater for different needs. First class has the fewest number of seats, and it caters for those who can afford and want to fly in luxury. Business class, on the other end, as the name says it, caters for those who want to fly and work at the same time. While the seats are more than first class, they are less than economy seats. And I don't think I have to explain economy. I mean, that is where the bulk of us belong. The seats are crammed, they can barely recline, but the cost is the most attractive part. You have options when you're purchasing a ticket. It just depends whether you're concerned about cost, comfort, or privacy. IP addresses have 5 different classes. We have class A, B, C, and D. But we're going to be focusing on the first 3. The last 2 are reserved for special addresses. So let us look at the different classes. Class A was designed to support large networks with over 16 million hosts. These addresses were allocated to big internet service providers who would then break them down into smaller networks and sell them to their customers. A Class A address uses the first 8 bits or the first octet of the IP address for the network ID and the remaining 24 bits for the host ID. This means that we have fewer networks with a maximum of 128, but each network has plenty hosts. On the screen, we have 2 diagrams. There is one that shows the network ID and host ID split for each class, and the other one shows the number of networks and hosts per class. These are basically there to help you visualize the difference between the classes. A class A address consumes almost 50% of all the entire IP addresses. Later on in the course, we're going to look at how mathematically we arrived at those numbers. A class A IP address range starts from 1 up to 126. So any IP address that starts with any of those numbers will belong to this class. This is similar with the flight. First class seats will probably be 1 to 10, business class from 11 to 29, and then from 30 to 200, that would probably be economy class. Okay, let's look at class B. This was designed to support the needs of moderate to large size networks that could have up to 65,000 hosts. A class B address uses the first 16 bits for the network address and the remaining 16 bits for the host address. You can have more networks over 16,384, and each network can have up to 65,000 hosts per network. So more organizations could apply for a class B block of addresses, and they consume almost 25% of all IP addresses. The easiest way that you can identify a class B IP address is it starts from 128 up to 191. And the last class that we're going to look at is class C. This was designed to support smaller networks with a maximum of 254 hosts. Class C addresses use the first 24 bits for the network address and the remaining 8 bits for the host address. This means that you can have up to 2 million networks, and each network having up to 254 hosts, and they consume about 12.5% of all the IP addressing. And the best way to identify that is any IP address that starts with 192 up to 223 will be considered a class C address. Class D is used for multicast, and class E is experimental blocks. But as we mentioned earlier on, we're not going to be focusing on those classes. These classes were known as classful addresses, and they were not flexible. They came in blocks that you could not change, and this caused a problem. In the next video, we're going to cover the problem more in detail. Thank you for watching, and I will see you in the next one. Classful addressing was good, but had the challenge of wasting IP addresses. Remember, our organization had to apply for IP addresses with an internet registry. If a company went to buy a block of IP addresses, they only had 3 options. Class A, which gave them 16 million hosts, Class B with over 16,000, or buy a Class C with only 254 hosts, and there was nothing in between. So a company that only required 2,000 addresses would be forced to buy a Class B block with over 16,000 addresses. A Class C address block would have been too small because it only had 254 hosts. So to put this into context, I want you to imagine going to a shop to buy a pair of jeans, and there are only 3 sizes: large, small, and extra large, and there's nothing in between. That would be ridiculous. So shops have solved this problem by making sure that they have jeans in almost every size, so that you and I can get a size that fits us. A system called Classless Interdomain Routing, or CIDR, was developed as an alternative to the traditional subnetting. This meant that they abandoned the network classes, and you could add a specification in the IP address to identify the number of bits that you're going to use for the network portion. Instead of being tied down to the traditional /8, /16, or /24, you could choose a variable length subnet mask. So what does this mean? If we look at an example, CIDR IP addresses are composed of 2 sets of numbers. We have the IP address, and then we have the slash notation. In this case, it's /22. That 22 indicates how many bits are being used to represent the network ID. So that slash notation can be adjusted depending on the size of the network. Earlier on, we saw that a Class C address used the first 24 bits for the network ID and the last 8 bits for the host ID. 2 to the power 8 gives us 256. This meant that a Class C network could only support 254 hosts. If we needed more than 254 hosts, with the slider notation, all we have to do is just move the subnet to a /23, which then gives us 23 bits for the network ID and 9 bits for the host portion. 2 to the power 9 is going to give you 512. So we have 510 hosts for that particular network. And this was not possible with Classful addressing. So when you go to an ISP, they will give you a block of IP addresses, and it will look something like this: 192.168.100.0/28. The slash notation tells you how many bits will be ones or turned on, or the ones that are going to be used for the network ID, and in this case is 28. And the rest of the bits that are not turned on or that are zeros are going to be used for the host ID. This means that the number of hosts per network can now be adjusted to meet a client's requirement, resulting in little or no wasting of addresses. Let us look at our default subnet mask for a class A address. It is 255.0.0.0. Converting that into binary, you will notice that the first octet is all ones, hence it's a /8. When referring to CIDR notation, we need to count all the ones to figure out the subnet. So 255.0.0.0 will be a /8 because it has the first 8 bits as ones. A class B subnet of 255.255.0 would be a /16 because when we convert that address into binary, you will notice that the first 16 bits are ones and the last 16 bits are zeros. So to simplify this, we're going to look at a CIDR block table that is going to provide a good overview to help us put this all together. We have the column that represents the subnet mask, and the second column is going to represent the equivalent in CIDR notation, and the third column is the number of hosts per network, and the last is going to be the binary exponent. It's very important for us to be able to view all these things together. Now, you will notice that as the slash notation value increases, our subnet mask also increases. What do I mean? Let's look at a /8. We find that our subnet mask was 255.0.0.0, but a /9 has a subnet mask of 255.128.0.0. The more our slider notation increases, the subnet mask also increases with it. As the slash notation value increases, our hosts per network reduce. A /17 has 32,000 hosts per network, but a /22 only has 1,024 hosts on that particular network. This means that we are no longer tied down to the fixed subnets of Classful addressing. Earlier on, we looked at a company that required 2,000 addresses. In the old system, they would have been forced to buy a /16, but with the slider notation, the company can now purchase a /21, which gives them 2,048 addresses, giving them exactly the number that they need or somewhere within the significant ballpark. This limits the wasting of IP addresses. Classless addressing means that you can allocate addresses according to network requirements. So you can get a /28 address that will give you 32 addresses, something that was impossible with Classful addressing. Please go through the table and be comfortable because those sequences are important when you're trying to subnet your networks. CIDR allowed us to choose networks that were directly proportional to the IP addresses that we required and thus saved IP addresses. In some sectors, CIDR is actually credited for saving the internet and slowing down IP address depletion or exhaustion. Thank you for watching, and I will see you in the next one. This is the section that most people struggle with in networking. So I'm going to try and simplify it as much as possible. Subnetting, by definition, is the process of breaking down something big into smaller components. It could be land, food, or in our case, it's breaking down a large network into smaller networks. There are many reasons for subnetting, such as security, creating smaller networks that are easier to manage, traffic segmentation, and breaking down broadcast domains. In the case of land, property developers buy huge tracts of land and subdivide them into smaller stands, which they sell to end users. This makes land affordable for you and I to buy and build homes. Pizza companies do the same. They sell their pizza sliced so that it is easier to eat. Imagine trying to eat a hot pizza that is not sliced. It will probably be a nightmare. So the next time you have to subnet, I want you to think about pizza. When you're subnetting, there are a few questions that you need to ask yourself. How many parts or portions do you need? If you have 4 friends and you want to share a pizza equally, you're going to cut it into 4 slices. However, If you have 8 friends, then you would have to cut it into 8 slices. So the number of slices is based on how many people or how many pizzas you have. This is the same with networks. There are questions that you need to answer to help you subnet, such as how many networks do you need? How many hosts per network will you require? Those questions will determine how you're going to subnet your network. In the next video, we'll look at how we can subnet. Thank you for watching, and I will see you in the next one. There are many ways to subnet a network. In this video, I'll cover a method that I learned from one of the famous networking authors by the name of Todd Lamle. No copyright infringement is intended. I'm just trying to teach a method that I found simplest amongst other methods that are available to subnet. Todd, if you're watching, thank you for coming up with this method. Before we look at subnetting, we need to have a quick recap on the binary system increments. It is important once again for you to be comfortable with counting to at least 2 to the power 10 in your head without having to write it down. Remember, we are multiplying the value by 2 to get the next increment. 2 times 2 equals to 4, 4 times 2 equals 8. So I want you to close your eyes and try and see how far you can go. Let's begin. 1, 2, 4, 8, 16, 32, 64. Okay, I trust that you're able to complete it by yourself. So when we are subnetting, we are usually given a block of addresses such as 192.168.10.0. We need to take that network and then subdivide it into smaller networks. We subnet by borrowing bits from the host part of the IP address in order to divide our larger network into smaller subnetworks called subnets. Remember earlier on, we said that an IP address is made up of 2 portions. There is the network ID and then there is the host ID. We also learned that the subnet mask tells us which part of the address is the network and which part is the host. A class A address has a subnet mask of 255.0.0.0 and it uses the first 8 bits for the network address and the last 24 bits for the host ID. A class C has a subnet mask of 255.255.255.0 and in slider notation that's a /24, and it uses the first 24 bits for the network address and the last 8 bits for the host address. So when we are subnetting a class C address, our focus is on the 4th octet because that is the octet that signifies the host ID. This means that we only have 8 bits for that host ID. It is from that host ID that we borrow bits to create our subnet. So we're going to look at an IP address before and after subnetting. We notice that before subnetting, our IP address is broken into 2 parts. We have the network ID and the host ID. But after subnetting, we'll have the network ID, the subnet ID, which are the borrowed bits, and the new host ID. The original host ID has now been divided into 2 parts. There are 5 questions that are critical for us to answer before we can subnet. The first question is, how many subnets does the chosen mask produce? The second one is, how many valid hosts per subnets are available? The third, what will be the valid subnets? The fourth is, what will be the broadcast address for each subnet? And the last one is, what are the valid hosts in each subnet? I will break down these questions in more detail in the next video. Thank you for watching, and I will see you in the next one. In this section, we're going to cover the critical questions that we need to understand before we can subnet in more detail. So question number 1 is, how many subnets does the chosen mask produce? In order for us to know how many subnets we can have from a chosen mask, we use a formula, and the formula is 2 to the power x is equals to the number of subnets, where x is the number of borrowed bits or ones. And in our case, we are borrowing 3 bits. So x is equals to 3. Therefore, 2 to the power 3 is equals to 8. So if we borrow 3 bits, we can create 8 subnets. Since we are subnetting a class C address, we are interested in the 4th octet. So we're going to demonstrate and see the difference that happens before and after you borrowed your bits. The original class C subnet is a /24. So it uses the first 24 bits for the network ID and the last 8 bits for the host ID. Now the original host ID is all zeros and it looks something like this. But because we are borrowing 3 bits. For every bit that we borrow, we're going to change the value from a 0 to a 1. After we have borrowed the first 3 bits, our host ID is going to be different and is now going to look something like this. The first 24 bits are for the standard Class C subnet. But now we have 3 new borrowed bits, which makes it 24 plus 3, giving us 27 ones. And we have a remaining 5 zeros or unborrowed bits. So our new network ID is now a /27 and our host ID is now 5 bits. Remember, an IP address is 32 bits, so that is the maximum number of bits that we can have. How many hosts can we have per subnet? And the formula for this one is 2 to the power y minus 2, where y is the number of unborrowed bits or zeros. In our example, we borrowed 3 bits out of 8, so we had 5 unborrowed bits. Therefore, y is equals to 5. 2 to the power 5 is equals to 32, minus 2 is equals to 30 hosts per subnet. The reason why we separate 2 is because there are 2 addresses that we need for every subnet, known as the network and broadcast address, and these cannot be assigned to hosts. Now, a point that you need to note, unborrowed bits are the same as unmasked bits. The terms are interchangeable. Sometimes you'll find other books will call them masked and unmasked bits, but they're basically the same as borrowed and unborrowed bits. So borrowed bits is equals to masked bits, which is equal to ones. Unborrowed bits is equals to unmasked bits, which is equals to zeros. Sorry, it's not the most simplest way to pronounce. Unmasked bits. Yes, unmasked bits. Question number 3. What are the valid subnets? This basically tells us where our networks begin and where they end. The formula for this is 256 minus the subnet mask is equals to the block size or the increment number. So to get our subnet mask, we need to write the address in binary and add all the numbers with the 1 below. That's why earlier on I kept on emphasizing that you need to be comfortable converting numbers from decimal to binary and binary to decimal. So if we look at our host ID, we are using the first 3 bits. So when we add 128 plus 64 plus 32, we get 224. So our subnet mask is 224. When we separate that from 256, we get 32. So our networks have a block size of 32 or increase in 32s starting from 0. So you have 0, 32, 64, 96, 128, 160, 192, and 224, giving us 8 networks. Question 4 is, what is the broadcast address for each subnet? Broadcast address is the number right before the next subnet. In our example, the first subnet was 0 followed by 32. So the number before 32 is 31. So 31 is the broadcast address for the 0 subnet. 63 will be the broadcast address for the 32 subnet. And the last broadcast address is always 255. I have put a line diagram to help us visualize. Our networks are increasing in 32s. So the first block is 0, 32, 64, 96. And the broadcast address is always the address before the next subnet. So the broadcast address for subnet 1 is 31. For subnet 2 is 63, for subnet 3 is 95, and for subnet 4 it is 127. The last question is, what are the valid hosts? These are the numbers between the network and broadcast address. So in our example, 0 is the subnet address, 31 is the broadcast. So 1 to 30 are the valid hosts in that particular range. All these concepts will become clearer when we look at examples. Earlier on, we looked at the questions that you need to answer in order for you to subnet. This time around, we're going to look at an example, and we've been given a network block of 192.168.10.0 with a subnet mask of 255.255.255.128. With this information, we need to go and figure out the rest. So to answer our question, we need to convert our decimal 128 into binary first. And 128 in binary is equals to 10000000. So we're only borrowing 1 bit from our host ID. So the formula to calculate the number of networks that we can create is 2 to the power x, where x is the number of borrowed bits. And in our case, it's 2 to the power 1. So we can only create 2 networks. The second question that we need to answer is, how many hosts can we have per subnet? And remember, the formula was 2 to the power y minus 2, where y is the unborrowed bits. And in our case, we borrowed 1 bit and we have 7 unborrowed bits, which are the zeros that we find in our binary address. So 2 to the power 7 minus 2 is going to give us 126 hosts. So we can only have 2 networks, and each network will have 126 hosts. The third question is, what are the valid subnets? This is the increment of your networks. And the formula was 256 minus the subnet mask. And in our case, it's 128. So 256 minus 128 gives us 128. So our networks are going to be increasing in 128. So the first network is going to be the 0 network, and the next one is going to be the 128 network. Those are the 2 networks that we're going to have in this case. The fourth question is the broadcast address. Remember, we said the broadcast address is the number before the next subnet. And in our case, 127 is the number before 128. So the network address for the 0 network, the broadcast address for the 0 network is going to be 127. And the broadcast address for the 128 network is going to be 255. And the last question is the number of valid hosts. These are the numbers between the network and the broadcast address. So for the 0 network, it's going to be 1 to 126. And for the 128 network, it's going to be 129 to 254. So this is how we break down or subnet an IP address block and get the different information to answer the 5 questions that we're basically looking for. I've included a table where I've tried to give the subnet, the first host, the last host, and the broadcast address. I've also included a logical diagram on how you depict this in a network, separating the subnets between the 2 particular networks. Let us look at another example. This time around, same network address, but the subnet mask is 255.255.255.192. The first thing we need to do is to convert our decimal 192 into binary. And if you remember, 128 plus 64 gives us 192. So we are borrowing the first 2 bits of the host ID, and we have 6 unborrowed bits. So how many subnets? 2 to the power 2, which is equals to 4. So when we borrow 2 bits, we create 4 networks. How many hosts per subnet? What is the number of unborrowed bits? 6. 2 to the power 6 minus 2 is 62. What is the increment of our subnets, or what are the valid subnets? Formula is 256 minus subnet mask. In our case, is 192. So 256 minus 192 is equals to 64. So our networks are going to start from 0, and they're going to increase to 64, 128, and 192. What is the broadcast address? What is the number before 64? 63. What is the number before 128? 127. What is the number before 192? 191. So those are going to be the broadcast addresses for our different subnets. What are the valid hosts per subnet? These are the numbers between the subnet and the broadcast address. For the 0 subnet, it's going to be 1 to 62. For the 64 network, it's going to be 65 to 126. A /26 mask gives us 4 networks, and we need a layer 3 device such as a router to connect between different subnets. So on our router, we're going to have 4 networks. So that is how you would represent that as a logical network diagram. So I'm hoping that we're starting to get a picture on how we would subnet an IP address when we are given the information and we need to break down and answer the 5 questions. These are the questions that you're going to be asking as you try and break down your network for different reasons. To reinforce this information, we're going to look at one more example. This time we should now be comfortable, so we're going to try and do this much more faster. Our subnet mask is 255.255.252, or it's a /30. So the first step is convert the decimal 252 into binary, and we're going to have 111111100. So we are borrowing 6 bits. First question, 2 to the power 6 is equals to 64. So we're going to have 64 subnets. The second question, number of hosts per subnet is 2 to the power 2 minus 2, which is equals to 2 hosts per subnet. So in this case, we're going to have 64 networks, but each with 2 hosts. What are the valid subnets? 256 minus 252 gives us 4. So our networks are going to increase in 4s. 0, 4, 8, 12, 16, 20, 24, 28, 32. What is the broadcast address? This is the address before the next subnet. So in our case, for the 0 network, 3 is the broadcast address. For the 4 network, 7 is going to be the broadcast address. For the 8 network is going to be 11. For the 16 network is going to be 19. And the valid hosts are the numbers between the network and the broadcast address. So for the 0 subnet, it's going to be 1 and 2. For the 4 network, it's going to be 5 and 6. These subnets are used for point-to-point links in networking. The reason being that point-to-point links support only 2 IP addresses. So you don't waste any additional IP addresses. Now, if you're someone like me, you probably would have observed that there's a pattern between borrowed bits, side annotation, and the subnet value. When you borrow 1 bit, you create 2 networks. When you borrow 2 bits, you create 4 networks. So the more bits you borrow, your subnets increase, but your hosts per subnet decrease. So if you're going to memorize this table, the next time you see a /25, in your mind, you're going to know that that is 2 networks, each with 126 hosts. When you see a /26, you're going to know that it creates 4 networks, each with 64 hosts. A /27 is going to be 8 networks, each with 32 hosts. So the moment you see a subnet mask, automatically in your mind, you're going to know how you're going to break it down. But this takes practice. Now that we are comfortable with subnetting on paper, we can now try doing it in the head or in your mind. Make sure that you don't have any paper near you. It might seem impossible at the beginning, but with practice, you should be able to nail it. I'm going to provide a link to the book for anyone who wants to reference it later. Similar to previous examples, we are given the IP address and the subnet mask, and we need to find out the other information, such as number of hosts per subnet, broadcast address, etc. So we need to start with the information that we know. In our case, our IP address is 192.168.10.33, and the subnet mask is 255.255.255.224. So step 1, we need to determine the subnet and broadcast address. And we're going to do this by answering question 3 of our 5 questions, which is looking for the valid subnet. And the formula is 256 minus the subnet mask. And in our case, 224 is the subnet mask. 256 minus 224 is equals to 32. So our networks are going to be increasing by 32s. Now, I want you to encourage to draw a line chart or line graph, I don't know, whatever you want to call it, and write your networks 0, 32, 64, 96, 128, 160, because these are our subnets. And then look at your IP address and see where the 4th octet sits. And in our case, the 4th octet is 33. And 33 falls between 32 and 64. So the 33 IP address is going to be part of the 192.168.10.32 subnet. The broadcast address is going to be the number before the next subnet. And in our case, it's 63. And the valid range is going to be from 33 up to 62. Very simple, right? Let us look at another example. 192.168.10.33. So the IP address is still the same, but the subnet mask is now different. We're now dealing with a .240 subnet mask. Once again, draw a line graph, line chart. Answer question number 3. 256 minus 240 is equals to 16. So our networks are going to increase in 16s. Write 0, mark 16, 32, 48, 64, 80, 96, because these are our increments. And then we go back to the IP address. Where does 33 sit? It sits between 32 and 48. Therefore, it belongs to the 32 subnet. What is the broadcast address? It's going to be 47 because the next subnet is 48 in this case. And our valid host range is between 33 and 46. Seems very straightforward. I promised you, the moment you master this process, subnetting is going to be very, very, very easy for you. Now that we have completed subnetting of a class C address, we are focusing on the 4th octet, and we're going to move on to the class B address. And the process of subnetting is pretty similar, except you are going to have more host bits, and you're going to start in the 3rd octet, and the rest is the same. So let us look at an example. We have a network address of 172.16.0.0, and the subnet mask of 255.255.128.0. And our interesting octet is going to be the 3rd one. So how many subnets? We convert 128 into binary, and we are borrowing 1 bit, and we have 15 unborrowed bits. So 2 to the power 1 is equals to 2. So we're going to create two networks. How many hosts per network? It's going to be 2 to the power 15 minus 2, which gives us 32,766 hosts. So we're going to have two networks, each with 32,000 plus hosts. What are the valid subnets? 256 minus 128 gives us 128. So our networks are going to be increasing in 128, with 0 being the first and 128 being the second one. What is the broadcast address? Earlier on we mentioned this is the number before the next subnet, but because we are starting from the third octet, for the 0 network, the broadcast address is going to be 127.255 because that's the number before the next network. And the broadcast address for the 128 subnet is going to be 255.255. What are the valid hosts? These are the numbers between the subnet and the broadcast address. And for the 0 network, it's going to be 0.1 to 127.254. And for the 128 network, it's going to be 128.1 to 255.254. I have provided a table that helps to visualize the start address, last address, and the broadcast address for the respective subnets. And because this is a /17, if you're going to draw it as a logical diagram, you're basically splitting the networks into two on your router interfaces, and you're going to have either of the two subnets on one end of your router. One more example, network address 172.16.0.0, but this time around our subnet mask is 254. The third bit is the interesting octet. So we need to convert 254 to binary, and that is 2 to the power 7 because we're borrowing 7 bits. And 2 to the power 7 is equals to 128. So we're going to create 128 networks. How many hosts per network? 2 to the power 9, which is the unborrowed bits, minus 2 is equals to 510 hosts. So you're going to have 128 networks, each with 510 hosts. What are the valid subnets? That's 256 minus 254, which is equals to 2. So our networks are going to start from 0, and they are going to increase in twos. So 0, 2, 4, 6, 8. What is the broadcast address? The number before the next subnet. In our case, our broadcast address for the 0.0 network is going to be 1.255, and the broadcast address for the 2 network is going to be 3.255. What are the valid hosts? These are the numbers between the subnets and the broadcast address. So for the 0.0 subnet, it's going to be .1 up to 1.254, and for the 2 network, it's going to be 2.1 to 3.254. Once again, I have included a diagram to help you visualize, and I've also included the logical drawing that you would have if you're going to put this in a network diagram for your network. We have observed that yes, subnetting a class B address might seem a bit tedious, but the principles are the same. It's just that we are dealing with more host bits because now we are dealing with 16 bits instead of 8 for the host ID that we were when we were using a class C address. But the moment you learn and understand how to do a class C, a class B is always going to be the same. You can take the same knowledge, the same process, and apply it onto class A addresses. Remember, you need to be able to master your CIDR notation table and how it increases, and also have an understanding of your binary increments, because that is going to guide you and help you as you practice and become comfortable in subnetting. There are two sides to working with IP subnetting in an enterprise environment. Number one, you have the operational view and you have the design perspective. The operational perspective is when you join an organization that already has an IP scheme that was designed by someone else. The design perspective is when you are hired to design the scheme based on the needs of the organization. In order for you to fully understand IP addressing and subnetting, we need to think about it from both a design and an operational perspective. Let us look at a design example. You have been hired as a consultant by Acme Corporation. They have moved into a new office block and they're going to be occupying 4 buildings. And they have the following needs. You've been given the following address 192.168.20.0/24, and it is your responsibility for you to subnet the different networks. Now, as you can see from our diagram, we need to ask ourselves the 5 questions of subnetting. In this case, we are going to need 7 networks, 4 for buildings A, B, C, and D, and 3 point-to-point links between the routers. The first question that we need to answer is, How many bits do we need to borrow to get 7 networks? Remember, our formula is 2 to the power x, where x is the borrowed bits. If we borrowed 1 bit, 2 to the power 1 is equals to 2. 2 networks are not enough. If we borrowed 2 bits, we're going to get 2 to the power 2, which is equals to 4, and 4 networks are not enough. However, if we borrow 3 bits, 2 to the power 3 is equals to 8, and 8 subnets meet our requirements of 7 networks. Next, we're going to look at how many hosts can we have per subnet and if it meets our design brief. Remember, the formula is 2 to the power y minus 2, where y is the unborrowed bits. In our case, we borrowed 3 and we have 5 unborrowed bits. So 2 to the power 5 minus 2 is equals to 32 minus 2, which is 30 hosts per network. When we look at our requirements, building D has the highest number of hosts at 28. So 30 hosts is going to be enough, but there's going to be very limited room for growth. Our block size is going to increment in 32s. The formula was 256 minus the subnet mask, and in our case, it is 224. And 256 minus 224 is going to give us 32. So our networks are going to increase in 32s. 0, 32, 64, 96, and 128. When we're done designing our IP scheme, it's going to look something like this. And this is how I would document my logic or subnets in a diagram format. You can write them in a table format. There is no preference. Choose an option that works for you. Now, whilst this design works, you notice that we are wasting a few addresses. If you observed, all subnets are using a /27 with equal number of hosts per network. We use the same subnet mask for each subnet to simplify the design process. However, it is wasteful because it is using more IP addresses than are necessary. If you look at our point-to-point links, they only use 2 addresses, but we've allocated them a subnet with 30 hosts, wasting 28 addresses. Building A and D have very little room for growth. This would be a bad design because the scheme is not catering for any future growth. In the next video, we're going to look at how we can solve this problem. In the previous video, we covered our first IP address scheme design. However, we noticed that our design was flawed and wasted IP addresses. VLSM, which stands for Variable Length Subnet Masking, is a subnet design that uses more than one mask in the same network. We can divide an IP address space into subnets of different sizes and allocate them according to the individual needs of a network. This type of subnetting makes more efficient use of IP addresses. Let us look at our previous example. We have already established that we need 7 networks, and because the hosts per building are different, we're going to calculate the subnets per building separately. Building A needs 25 hosts, and the closest network that can give us more than 25 hosts will be a /27 network. We know that from past examples that a /27 network has got 5 unborrowed bits. 2 to the power 5 minus 2 is going to give us 30 hosts, and 30 hosts do exceed the 25 that are required in building A. The block size is going to be 256 minus 224, which is going to give us 32. So it's going to increase in 32s. So our first subnet is going to be 192.168.200.0/27. Building B needs 20 hosts. So we're going to use a /27, which will give us 30 hosts, and our network address is going to be 192.168.200.32/27. Building C needs 15 hosts, and we're also going to use a /27 because the /28 will be too little. So our network address is going to be 192.168.200.64/27. So you will notice that now our networks are increasing in blocks of 32. However, building D needs 28 hosts, and we could use a /27 subnet, but we're only going to remain with 2 free IP addresses, and that leaves us with very minimal room for growth. So we're going to use a /26 so that we can cater for any future growth. In a /26 network, we're going to be borrowing 2 bits, and we're going to remain with 6 unborrowed bits. 2 to the power 6 minus 2 is going to give us 64 minus 2 is going to give us 62 hosts. So we're going to allocate building D up to 62 hosts, and that block size is going to increase by 64. Therefore, our network for building D is going to be 192.168.200.96/64. 26. Our point-to-point links only utilize 2 IP addresses, so we're going to use a /30 mask. Since they have a block size of 4, we will use 192.168.200.160/30 between R1 and R2, and we use 192.168.200.164/30 between R2 and R3, and then 192.168.200.168 between R3 and R4. Now you'll notice that this leaves us with extra subnets for future growth. So when you use variable length subnet masking, it allows us to preserve or shrink and expand each subnet based on the requirements of that particular network. After we have completed subnetting, our logical diagram is going to look something like this. We no longer have one subnet mask across all our networks, but we have adjusted the masks in accordance to the network requirements. VLSM makes more efficient use of IP addresses, and it is the de facto standard for how every network is designed today. We started this section by looking at what is subnetting. We then covered how to subnet, and we looked at the various techniques to subnetting. We then closed by designing our own IP scheme. Whilst the IP schemes in an enterprise environment are more complex, the principles are always the same. So if you have an understanding of subnetting a simple network such as this one, you can carry the same principles and implement them in a corporate environment. Earlier on in the course, we checked the IP address on our computers. This time, we're going to be configuring the IP address. There are 3 ways that a computer gets an IP address. Number 1 is dynamic. These are addresses assigned by a DHCP server. You get issued a lease for a period of time, and the address changes when the lease expires. This is the default on Windows machine. The second one is static. This is when you hard code the IP address on the device, and this address doesn't change unless you manually change it. The third option is known as automatic private IP addressing, or APIPA. This option is not good. When you see yourself getting this address, then you know things are wrong. This address is only issued when the computer cannot reach the DHCP server, and it usually starts with 169.254. If you want to change the IP address on your Windows 10 machine, you go to Control Panel, Network and Internet, Network Sharing, change adapter settings, find the network interface card that you want to change. When you have located it, right-click on the network card and go to Properties, and you select IPv4, and in there you are going to find the configuration that you can make to change between static and DHCP. If you want to allocate a static IP address, then enter your IP address, subnet mask, default gateway, and DNS settings. Click OK, and you have assigned yourself a static IP address on your PC. Make sure that you have your settings correct. Most network issues are due to misconfiguration of static configurations, such as putting the wrong mask or the wrong default gateway or pointing to the incorrect DNS server. Later on, we're going to look at the IPconfig command that allows us that visibility to see if our settings are correct. A good plumber or electrician carries with him all the tools necessary to do the job. Every network engineer or administrator has a set of tools that they use to troubleshoot network issues. These tools are very important because they help us to quickly establish root cause to our network problems. The tools come with an operating system and you do not need to install anything. The following are the 3 most important tools. Number 1 is ping. This is probably the number 1 utility that nearly every network professional uses on a daily basis. Ping is a utility that is used to test reachability of a host on an IP network. The command works by sending packets of data to a specific address and then lets you know how long it took to transmit the data and if it got a response. When you get a reply, it means that there is connectivity between your device and the remote device. But when you get a request timed out or destination host unreachable, then there are likely problems on your network. When ping returns data on how long it took to transmit, it returns that information in milliseconds, also known as latency. Latency can be an indication of your network performance. High latency could mean that your link is saturated, or your wireless network has got weak signals, or maybe you're experiencing a bad network cable. So there's a lot of information that we can collect from the ping command. So how do we use the ping command? All you need to do is go into command prompt on your Windows machine. I think we covered that earlier on. And then you can ping the destination address. You can either use the IP address or the host name, and you should be able to get a response. By default, ping sends 4 packets, and it gives you the statistics based on that. In my case, I sent 4 and I received 4 and I lost 0. So my network is working 100%. We've looked at this command earlier, but this time around we're going to look at an extension of the command that gives us a whole wealth of information. We can get the make and model of our network card. We can get the MAC address, also known as the physical address. We can get our IPv4 address, subnet mask, default gateway, DNS. We can also find out whether we are getting our IP address via DHCP or static. In the case of DHCP, you can get information on the leases and when they expire. All this information is very crucial when you're troubleshooting issues. And depending on the nature of the issue that you're troubleshooting, the information that you get from the IPconfig command is going to be very vital. So the command that you type is IPconfig // ALL, and you press enter. The last tool that we're going to cover is traceroute. Traceroute is a network diagnostic tool that is used to track in real time the pathway taken by a packet on an IP network from source to destination, and reports the IP addresses of all the routers along the path. Traceroute is a useful tool for determining the response delays and routing loops present on your network. It also helps you locate any points of failure that might have been encountered en route to your certain destination. Most of the times we use the command to try and establish where we are experiencing latency on our network or along the path to our destination. And we can use that information to benchmark and try and establish if there's any issues on the network. You type the command in command prompt and you can trace once again based on the IP address or the host name. I want you to practice this on your computer. I want you to trace the path from your PC to the IP address 8.8.8.8, which is the famous Google DNS. There are many tools that you can use to troubleshoot issues, but these 3 are the most important and will help you narrow down your problems. If you can master the content that we've covered in this course, then you're on your way to mastering IP addressing. The fundamentals are always going to be the same despite the size of a network. The formulas that we covered will apply to a 100 host network and will also apply equally to a 65,000 host network. So the size does not matter because the principles are always going to be the same. I hope you found value in this course. I want to thank you for watching, and I will see you in the next one.